we now at Silixa have a wireline deployed cable that we can put in and be able to monitor hydraulic fractures and optimize the designs. So briefly, I'll go over the agenda here. Why perform Crosswell monitoring, some of the historical challenges associated with that with fiber optics, what is high precision engineered fiber technology, and then we'll go right into some of the services and deliverables that we have. So first of all, why perform Crosswell monitoring? Well, as an industry, we've come a long ways. I was talking to an operator just the other day, and they're going to drill a 15,000-foot lateral in 9 days, and then complete with 12 stages a day. So from an efficiency standpoint, we've come a long ways as an industry. But the key to unconventional reservoirs, as pointed out in the previous talk, is understanding what we're doing in between the wells and the stimulated reservoir volume. And are we overstimulating? Are we understimulating? Are we getting frac hits that we may not want? Or are there some that we do want? So, historically, we've had a certain number of tools in our toolbox to be able to measure that, like Microseismic, tilt meters, tracers, etc. So fiber optics has entered the realm of monitoring here over the past few years, and it has had some challenges associated with it. The first one is cost. When I first came into Silixa, the two things I heard from every single operator is how do we reduce the cost and how do we get deliverables on time. And what you'll see here today is we're addressing both of those key issues. So in a permanent installation, as you know, the costs can be quite high, anywhere from $1 million to $2 million for a project. And typically you only have one cable to be able to monitor. So that gives you limited applications to some of your data. You get good allocations of the permanent and good production data. Microseismic with a single cable with DAS has been a challenge. But now we have another option is to be able to deploy a wireline cable in an adjacent well, and that gives you the ability to do that at a lower cost without involving any of the drilling risks or hazards or the potential of perforating and breaking that cable. So that gives us a lot more flexibility. And in the grand scheme of things, the technology that enables that is an engineered fiber, and in Silixa we call that Carina sensing system. If you look at a standard fiber, you want to be able to get enough light down and get reflectivity coming back, and that gives you your signal to noise. So there's a balance there to be able to get enough light down and enough light back to get a good signal to noise. With an engineered fiber, what we do is we create bright scatter centers that give us a higher reflectivity coming back, and combine that with an interrogator, and that gives us about 100-fold improvement in our signal to noise. And what that does for us is, if you look at the graph on the left, the upper blue curve is the noise floor for standard DAS technology. The other curves below that are geophones, and the one at the bottom is the Carina the precision engineered fiber. So it gives you a much lower signal to noise. And the graph on the right was acquisition in our test loop in London. And you can see that pink area on the right graph is all of the signal that we can now see because we have a lower floor noise and better signal to noise. So we can see things quite literally that we've never been able to see before, and that gives us the technology to be able to deploy this on a wireline and have good results. Here's an example of seismic, where on the left we have geophones, and In the middle, we have the standard DAS. On the right-hand side, we have the engineered fiber, the Carina engineered fiber. And you can see that with the same number of sweeps, we get very good, very high fidelity seismic, which helps with the efficiency as well as the interpretation of the data. Now, the new piece of this is being able to do it with a wireline. A little over a year ago, we did a test just by simply pumping down a wireline cable in an adjacent well to monitor the frac operations, and we call the service Carina XwellXpress. And by doing that, we were able to collect really high-quality strain and microseismic and VSP in those wells. This is an example of the operation on location. Typically, we'll have one to two trucks out there where we can either pump down or tractor down in a well, and we've literally done, monitored thousands of stages now. The other piece that I talked about earlier was how can we get deliverables in a timely manner to be able to action them at the well site. So we've taken all of our processing to the well site and developed software to be able to get deliverables either right after the stage or during the stage. So Crosswell strain is becoming a big tool in helping define, helping monitor fracs and completions. This is an example on the left where you have a horizontal frac well in a stage that you begin pumping. And the typical thing is when you start pumping, you induce stress in the rock. Well, that stress can be seen quite quickly and immediately in the horizontal monitor well a distance away. You can see that first stress is a poroelastic effect. Then as you crack the rock and break it, you get this compression, tension compression as you initiate that frac, and it goes across the monitor well. And then as you stop pumping, that reverses. So this illustration is just to show as you start pumping, you see that poroelastic effect at the front of the strain. And then as those fractures cross the monitor well, then you can easily see those and look at and pick out individual frac hits. So this is really becoming a big tool that we can actually measure the time, distance, and depth of these frac hits on monitor wells now. Now, the question that we always get is how does it compare to a permanent install? So we had an opportunity to put the wireline deployed one in a well where we had a permanent, and this is the comparison. You have the wireline on the left and the permanent on the right. And as you can see, the wireline gives quite good data. In some sense, it looks like it has even more sensitivity on there. Part of that could be the deployment mechanism and the fact that permanent cables do have the polyurethane on the outside, but regardless of that, you get quite good data, and we literally have hundreds of these stages and thousands that we've monitored now, and it's very consistent. So what can you do with that data? Now that you have the ability to have more than one cable out there to monitor, we can put a cable further away and up, maybe up in an upper zone, and you can see that you can just see this poroelastic effect. So what that means is that you can see the stress in the rock, but that frac really hasn't hit that well, come across that well. In this next slide, the well is on the same level and closer, and we can still see this poroelastic effect, but now we can see definite frac hits as they come across the well. So by doing that, by having multiple distances, you can now look at your frac models and calibrate them as you get the data. This next one is an example of the software that we use on location. On the upper left, we have the strain. just below that we have the pump data, and the middle sections are the strain curves associated with the strain waterfall on the left, where you'll see blue is compression, red is tension, and blue compression. And then we have some other features there, and we're able to map these frac hits with time and distance and depth, and output a table below. And then once you have that, you can then put that into your 3D, whatever modeling software you're using, and be able to map your frac hits and redo your completion models, your frac models. This next slide is an animation of that. And okay, if you have three different monitor wells, you can see again the ability to get different distances. And this is an example of, as we run through the software, we can pick the pump start time, we can pick the frac hit depth, and it all puts it out in this table below. So this happens right after the stage, so you're getting this data right after the stage, and you can use it as input to your next completion. Another, whoops, where are we going here? There we go. Another output that we have is we output a 12 or 24-hour plot where we can look at multiple wells, multiple stages. In this case, you can see well 1 and well 2, they're zippering these two wells. And you can see the strain effects on this. And this is pretty competent rock, so they look pretty consistent. But even as you look closer, you can see subtle differences in the closure, in the strain hits themselves. And as you change your designs and make some changes, you can definitely see patterns. If you have less clusters versus more clusters, you'll be able to see that on the strain a lot of the time. The other thing that we see with this plot is we can see interference. You know, in the previous talk, when they were talking about frac hits and interference patterns, sometimes we'll see one of these stages that reactivates the other stage. So it gives you a lot of information about how you're fracking and how that zippering operation is affecting the stimulated volume. The other piece of this is the Microseismic from the engineered fiber, the Carina Fibre, is pretty amazing. It gives you really high quality microseismic signals. This is a microseismic event. You can clearly see your P&S wave. We can also see reflected waves from previously fracked zones. And so, you know, this is, you know, reflected waves off a fracture plane. So, you know, going forward, we'll be looking at that as we get more and more data. But very high quality. We get microseismic locations. You know, in this particular project, we had 3 monitor wells. We had actually over 600,000 events and 280,000 co-located events. So you can imagine what you can do with that data and that data quality. And now we're getting to the point where we can do the microseismic and strain with auto picking in real time. And here's an example where we have a frac well on the bottom. The monitor well is in green, and we're combining the 2 data streams with the strain and the microseismic. So this is where you can see the strain hits on the monitor well. We're mapping the corridors in between the wells and how fast and where it hits that well. So that's your frac azimuth and your fracture corridor. And then you can bring in the microseismic to look at the total volume. And again, we're getting to the point now where we can do this on location at real time. So another application is vertical wells. So here's an example where if you look at the graph on the left, you can see this well that goes down below the other 3. This was a well that had been previously completed and produced. They pulled the tubing out, and then we drop the wire line in. You can see on the right-hand side the red where we drop the wire line into, and simply just dropped it in there and let it sit there. And as they tracked the other wells, we monitored those wells as they came across, and you can see in the middle we could see the Crosswell strain off those frac stages, as well as the microseismic on the right-hand side. And what's amazing about this is that this vertical well only has 2 degrees deviation, and we're seeing this through 2 strings of pipe. And that can only be done with the sensitivity that we have with the engineered fiber. It's just an amazing technology. So this gives you the ability to not only look in the horizontal, but to take a vertical and get track height and growth out of that. So flexibility. We look at projects now. We have to change our mindset. We can look at projects where perhaps you have a permanent installation because you want to understand your cluster allocation and some of your production later on. So that's a critical piece of information that we still need to gather. But now you can supplement that with a couple of different wireline deployed ones somewhere in your project. In this case, we can see that they did a couple tests and cluster tests on 1 and 2. And then once you finish that and finished your zippering operation, you can easily redeploy one of those cables to take advantage of it and look at the application on another pad or another area. So it gives you a lot of flexibility. You don't have to have it in a well for the entire frac. You can put it in for a few days, get the data you need, change your modify your completion design, and then measure it again on another area. So again, it gives a lot of flexibility and ability to get data and actually measure what you're doing. So with that, the value creation, again, the base of the pyramid is production. If we can use this type of technology to better understand stimulated reservoir volume, we can save money, but we can also help increase the productivity of the wells. As far as cost or risk, with the wireline deployed, it gives us the ability to not interfere with any drilling practices. It has flexibility, so it doesn't interfere with zippering operations and frac operations. It just gives you a whole nother dimension of being able to get these measurements and action on them. And with all of this, the deliverables are now on location, so you can actually make changes as you get the feedback, and you can actually change it on the project that you're on. So again, it gives you a lot of flexibility, and it's pretty exciting to be able to have another way to measure efficiently. So with that, I will close.